All right, ladies and gentlemen, welcome back to another video with Mr. Kenton in HL Chemistry, and we are in the home stretch of topic 1 in stoichiometric relationships, and we're going to be taking our final stop by looking at solutions and concentration and how we can do solution stoichiometry, as we've called it in the past. And so kind of our big principle, big idea here is understanding that the molar concentration of a solution is determined by the amount of solute and the volume of solution. Think about it. That's molarity, right? So let's just dive right in, guys. So we can think of concentration. It's the composition of the solution expressed in moles or grams of solute over volume of the total solution. Now remember, there are lots of different concentration units, but for chemists, the one that we use the most is molarity. Remember, there's also molality. You could think of it like from an environmental science perspective. It could be the parts per million or parts per billion of certain particles that are in maybe air or maybe even in water. You could start looking at those ppm or ppb values. Now, when no more solute can be dissolved in a solution, we say that that solution is saturated. So you think about how solutions form. You can have unsaturated solutions, saturated solutions, and supersaturated solutions. And so, the goal typically when you're making a solution is you're trying to get a specific amount of your solute dissolved in your solvent, right? And so, but we think of this process, this is an equilibrium process, but when no more solute can be dissolved in the solution, we say that solution is saturated. It can no longer hold any more of that particular solute. Now, when we start to look at concentration, if you remember, concentrations in terms of their units, or we could say the concentration of sodium chloride, we put sodium chloride in square brackets, then we're saying, okay, it's saying something about the concentration of sodium chloride, right? So square brackets are often used to represent molarity, or concentration. Now again, like we said, concentration is going to be moles of solute divided by the volume of the solution, and that's going to give us specifically the molarity of that particular solution. Now, from an IB perspective, concentration is usually given in decimeters cubed, which is, again, slightly different than what we're used to, but we can look at, and we've looked at previously, the conversion factor to where we can go from volume in liters to decimeters cubed and things like that. So this is just very much an IB thing, sticking with the SI units. And remember, to solve for moles, you just multiply the concentration by the volume that you've been given, and that'll take you into moles. Very common calculation, very straightforward. I have great confidence that you guys understand how to do that. Right? And so if you are asked or given a volume of centimeters cubed and asked to find the moles with a concentration using moles per decimeters cubed, you're going to have to divide that answer by 1,000, right, to get you into the proper units. So 1 decimeter cubed is equivalent to 1,000 centimeters cubed. And so having that conversion factor kind of rooted in the back of your mind could be very useful moving forward. All right, now when we think about units of concentration, we've got grams per decimeter cubed, aka grams per liter. You got moles per decimeter cubed, grams or moles per liter, and parts per million. Again, those are some different concentration units that you should be familiar with. And like we said, they have different uses. Obviously, the first two are going to be very indicative when we're talking about solutions. And then parts per million, that might be more prevalent in environmental science, where again you're looking at air quality or maybe even water quality, and you're looking at a particular substance, maybe a particulate or a solute or an ion that is in the air or is in your water, and you're testing that, and you might get that in parts per million. Again, we've mentioned you got to use square brackets to denote your concentration. And then, you know, when we've done labs in the past, typically what I will do is I will provide you guys with some sort of what we call a standard solution. And that's the thing that you know the concentration of, right? And you think about titration, for example. I give you a standard solution of sodium hydroxide. It's got a known concentration. You use that, and you use that standard solution to try to figure out something that is unknown. Like, for example, if you have an acid but you don't know the concentration, you use a standard solution of base, you titrate it, you can figure out that unknown's concentration of that acid. Another thing to note here as we're talking about solutions and electrolytes, right? So remember, strong electrolytes are assumed to completely break down into ions in solution. Remember, a strong electrolyte is something that completely dissociates or ionizes when it forms a solution. So you think about things like hydrochloric acid. When it's dissolved in water, it exists exclusively as H+ ions and Cl- ions. Or something like sodium nitrate, NaNO3. When it's dissolved in water, it exists exclusively as Na+ ions and NO3 1- ions in that solution. It doesn't stay together as NaNO3, right? And so let's take a deeper look into electrolytes now. Now, electrolytes, you know, you've seen the Gatorade commercials, all that fun stuff, but electrolytes are simply substances that when in a solution, they break down into individual ions, and they're able to conduct electricity due to the presence of those ions, because now those ions are freely moving about in the solution, and so electrical current can move through it. Now, for our purposes, all ionic compounds are electrolytes, meaning that when they're in solution, they dissociate into the ions that make up that compound. So for example, like NaCl, since it's ionic, we'd say that it's going to dissociate into Na+ ions and Cl- ions. Or let's think of something like ammonium acetate. It's going to break down into NH4+ ions and C2H3O2- ions when it's placed in solution, right? Now, your strong acids and your strong bases, they dissociate completely into their ions as well. So think of your strong acids like nitric acid, HNO3, or sulfuric acid, H2SO4, or even some of your strong bases like sodium hydroxide breaks apart into Na+ and OH-, or something like potassium hydroxide to make K+ and OH-. So keep in mind those types of substances are strong electrolytes. And remember, strong simply means it completely separates into those ions, okay? Remember, strength versus concentration, those are two separate things, right? That's kind of what I'm getting at here as I'm mentioning this. All right. Now, knowing that electrolytes break apart, what you should be able to do is if you have an electrolyte, you should be able to determine the concentration of the individual ions that are present in a particular aqueous solution. And so we're going to look at an example here on the next slide that should hopefully clarify what that looks like. So let's say, for example, you've got 1 molar HCl, right? 1 mole per decimeter cubed. Well, then the concentration of the individual ions, you're going to have 1 mole or 1 molar H+ ions and 1 molar Cl- ions. That's because HCl breaks down into both of those, and they take on the volume based on the stoichiometric relationships in the equation itself. There's 1H, so the concentration of H+ is equivalent to the molar concentration of the entire substance. And same thing with the chloride ions as well. Now, where this might be a little bit different is if you have something like barium hydroxide. So if you have a 2 molar or 2 moles per decimeter cubed solution of barium hydroxide, when you look at the barium, it's going to have a 2 molar concentration of barium 2 plus ions. But if you notice, you look at the hydroxide ions, it's got a concentration of 4 molar, or 4 moles per decimeter cubed. That's because you've got the original concentration of the solution, but then you have 2 moles of hydroxide ions. So you're going to essentially double the concentration of the hydroxide ions. Now, when you look at anything that's an ionic compound, you should be able to break it into its ions and then be able to determine the concentration of the individual ions based on the original concentration of the ionic compound. And so I hope that makes sense, ladies and gentlemen. That's all I wanted to take a look at as it pertains to solutions for now. And so thank you guys so much for taking the time to watch this. Hopefully this was insightful. Hopefully it was a good review for you. And I look forward to seeing you guys again soon. Take care.